we try to get rid of radicals and simplify the function. Okay. Yeah. So if you see a radical integral something like that, and then you probably just recall the formula. Okay. For example, integral of 1 minus x squared dx, and you know that this is going to be arc sine x plus constant. Okay. But besides this, you know, right? If you see something involves square root 1 minus x squared, you may not able to quickly find the antiderivative, okay, if it's not in this simple form. So how do we get rid of the radicals in order to simplify? We have a few identities we should know, okay? One is 1 minus sine square theta, and it's going to be cosine square theta, okay? Right? So if it's inside the radical, then you can get rid of the radical, right? It's become cosine theta. But this is true only for theta between pi over 2 and negative pi over 2. Similarly, we have 1 plus tangent square theta. Okay. 1 plus tangent square theta, and that is going to be secant square theta. So, so if you put a radical square root of this, and this will be just secant theta. I have to make sure theta is between pi over 2, okay? Secant theta. Because secant theta is positive for theta between negative pi over 2 and pi over 2. That's the first thing, right? Second. The third one is I switch the order, you know, secant square theta minus 1 equals tangent square theta, okay? Right? Then if it's inside the square root, then this will be tangent theta. And this one, I think we should, assuming the domain for the you know, this is where we define the arcsecant theta. So it's theta is between 0 and pi over 2, and theta is greater than pi less, greater than equal to pi less than 3 pi over 2. Okay, and this is a domain for the secant theta on which we define the inverse function. Okay, so those are the important identities. Okay, we are going to use to solve an integral. Okay, for example, okay, problems like that, you know, this one we have 2 options here to solve. Okay, one is just use a regular substitution. Okay, so you can let u to be 1 minus x squared, right? Then the reason I want to use this substitution because du is going to be negative 2x dx. Okay, so so the integral becomes square root u, right? And x times dx is negative 1/2 du, right? So this is a power function now. Okay, and then you find the antiderivative of that. Okay, so you will get negative 1/2, and that's negative 1/2 plus 1, u to the negative 1/2 plus 1, right? And plus constant. I think I'm going to get negative u to the 1/2 plus constant. Oops, my 5's gone, so just a second, okay? Sometimes it's happened. Yeah, this is called the instability of this program. Yeah, when you design something, right, you have to make sure it's stable. Sometimes when you touch a little bit, even any kind of machine, right, or equipment design, right, stability very important. I don't know. This is a software that came with a computer. Yes. So where are we? Okay. Let me quickly write down this. What do we get, right? So we got square root u and -1/2 du. Okay. So that is going to be actually is negative after, yeah, 1/2 u to the -1/2 du. Okay. Then I got -1/2 plus constant. Finally, I get -u to the 1/2 plus constant. Okay. So when you differentiate, you will get the same. Okay. Then you replace u by negative square root of 1 minus x squared and plus constant. Okay. So that, yeah, we can solve this problem without using any other special substitution. Now we can, okay, we can use try another substitution, because I know 1 minus sine square theta can be cosine square theta. So why not let x to be sine theta? This is another substitution, right? If you let x to be sine theta, then 1 minus x squared is going to be square root, right? It's 1 minus sine square theta, and that's cosine theta, okay? I have to assume that theta is between pi over 2 and negative pi over 2, okay? Then the integral becomes x is sine theta, okay? Square root of 1 minus x squared is going to be cosine theta, and the derivative of dx, right? Dx is a cosine theta d theta. That is dx. Okay. Okay, that is dx. Because x is cosine theta, so dx is sine theta, cosine theta. Then you see that cosine x is cancelled out. This is just integral of sine theta d theta. So the antiderivative of this is negative cosine theta plus constant. Now, cosine theta, already know that cosine theta is a square root of 1 minus x squared. So you have to change it to the radical, the square root of 1 minus x squared. Okay. And so for this problem, you have 2 different ways to solve it. Okay? Either of them works, but sometimes you're not lucky, you're not able to use a traditional substitution. You have to use this so-called trigonometric substitution. All right, let's try another one. I switch it. Yeah, look at this. All right, so I'll give you a little bit of time to think about it. Okay, so let me. Yeah, my suggestion is to use substitution. Right, and this problem may be related to the one we have. Okay, let's try. That's the reason I did not discuss the homework problem at the very beginning. Okay, so you see square root of 1 minus x squared, right? And I just cannot find any other substitution. So we try this substitution, let x to be sine theta, right? Then dx is going to be cosine theta d theta, right? And I hope you plug them into the formula, right? This is and then 1 minus x squared is going to be cosine theta, right? So this is a cosine theta, and this is a sine square theta, and the dx is a cosine theta d theta, right? All right. So now what? You get integral of cotangent square theta d theta. This is a problem section 7.235. This is a problem you asked at the beginning. Okay, right? This is the integral, right? If you know how to evaluate this integral, then you can solve the problem. All right, so what is the next step? So you have to know lots of identities in order to solve it, okay? It's different, if without this cosine theta, I can use a substitution, another substitution. Now there's a cosine theta square, and there's no way I can use the traditional substitution, trying to simplify it. Oh, I cannot even use the integration by parts. Okay, what is that? But for cotangent theta, I have another identity. It's get cosecant square theta minus 1 and d theta. Okay. Or if you don't like cotangent theta, you get cosine square theta over sine square theta equals 1 minus sine square theta. You can try this, right? Then you will get 1 over sine square theta minus 1. So that is a secant square theta, okay? Well, cosecant square theta. So it's the integral of a cosecant square theta d theta minus the theta, right? All right, now what is the antiderivative of the cosecant square theta? It is negative cotangent theta. Cotangent theta is going to be negative cosecant square theta, right? Derivative of tangent theta is going to be secant square theta, right? So those are the formulas. So therefore, the antiderivative is just cotangent theta, okay, minus theta, and plus constant. That's it. Good. So I solved this problem. I also almost answered the question you have, right? Yeah, 35. Now for the 35, actually this is a definite integral. The definite integral is going to be like that from pi over 2, pi over 6, pi over 2, okay? And then this is a cotangent square theta d theta. First of all, you have to make sure the function is defined on this interval, okay? Yeah, the function is defined on this interval. Cotangent theta, where's the cotangent theta defined? Take the picture. Cotangent theta is defined on this interval, I think, yeah. Tangent, cotangent, yeah. This is a graph for cotangent theta, y cotangent theta. So from pi over 6 to pi over 2, that is okay. Okay, cotangent, hold on, let me check, double check, okay. Cotangent, yeah, is going to be cotangent, no, it's my picture. Okay, cotangent, the denominator is a sine theta, okay, cotangent, okay. It's going to be cosine theta, sine theta, okay. So let me reschedule the graph. That's misleading, okay. Okay, first of all, it's defined on the interval from 0 to pi because sine theta is positive. When theta is getting close to 0, this became positive. When theta getting close to pi or 2, yeah, actually this is correct, yeah. So you just double check it on the possible values. Okay, but anyway, it's well defined. So we already know the antiderivative of this function, and then you put cotangent pi over 2 minus pi over 2 minus negative cotangent pi over 6 minus pi over 6. Okay, you have to evaluate cotangent pi over 2 is 0, right? So this first part is pi over 2, and plus cotangent pi over 6. Cotangent pi over 6, I think it is going to be square root 3, okay, because it's a sine pi of cosine pi over 6 divided by sine pi over 6. And that's only I remember, okay? So that should be square root of 3. And then plus it's positive, yeah, positive, negative, positive, okay? So that will be square root of 3 minus 2 pi over 6. Right, that's 1/3. Right. That's 1/3 of pi. And this should be a positive number. Right. If it's not a positive number, then it's wrong. All right. All right. Similarly, you can do the problem integral of tangent square theta d theta, right? And just because tangent square theta is going to be, right, is going to be secant square theta minus 1, right? Then the antiderivative secant square theta is going to be the tangent theta, right? Then minus the antiderivative 1 is theta, so it's plus constant. It's the same method. All right. All right, now we're going to look at some different problems. All right, I'm going to ask you to look at this. How can I evaluate this in? Right? You think about it, okay? All right, let's continue. Similarly, when you see x on the top, right, so that means you can use a substitution. You can use this substitution. Okay, so the problem can become pretty simple. So du equals 2x dx. Then the integral becomes square root u, and x times dx is going to be half of du, right? Okay, so it's going to be u to the negative half du. Okay, then you find the antiderivative of this. Antiderivative of this, it is going to be negative 1/2 plus 1, right? U to the negative 1/2 plus 1 and plus constant. Okay, and after you simplify, just u to the 1/2 plus constant. All right, then you replace u by square root of x squared plus 1, so x squared plus 4. So this is the answer, okay? Now, what I wanted to do actually here is to use a substitution. So use a substitution. All right, this time, how can I remember, right? Tangent square theta plus 1 equals secant square theta, right? So if you put a radical there, then you can get rid of the radical, right? No, and here theta should be less than pi over 2. Yeah, because when you use yeah, this is what we decide. We have to make sure theta is in the domain of the tangent function when we define the inverse, because eventually you have to let x to be tangent theta, right? Then you can solve for tangent, you can solve for theta, right? It's going to be tangent inverse. So you have to make sure theta is in this interval, okay? Then you can inverse to each other, because at the end you get a function with theta, but you have to replace it by tangent x, okay? So this is going to be here secant theta, right? And this will be tangent theta. Now derivative of tangent theta is c dx is going to be secant square theta d theta, right? All right, so secant square theta d theta. All right. So let's try to now forget, yeah. So here my substitution is not only just 2. I have to, that's not, that cannot change because there's x squared plus 4 here. So you already noted that problem, right? So what we should do is we have to put a 2 here, okay? And then this will be, theta will be half of it, arctangent half of x, okay? So dx is twice of secant squared d theta, okay? So twice of secant theta d theta, okay? And this is a 2 tangent theta, okay? And also the denominator is going to be 2 secant theta because if this is a 2 tangent square theta, right, and plus 4, you will get 4 secant square theta, you get 2 secant theta, okay? That's the reason. So 2 cancel out. So I get tangent secant theta canceled out, right? So what I got here is just twice of tangent theta, secant theta d theta. Now what is this? This is just a derivative of secant theta, okay? We have to know lots of formulas here, right? Derivative of secant theta is going to be tangent theta secant theta, okay? So that's why it's 2 secant theta plus c. But secant theta, what is secant theta, right? Secant theta, come on, secant theta is this one, okay? Right? 2 secant theta is just equal this. Right? And then we know that this is going to be x, 2 tangent theta x. Let's get constant. But this looks more complicated than the traditional substitution. Okay, so sometimes, yeah, if you use a trigonometric substitution, it becomes more complicated. It's possible. Okay. There's another one, right? I want to mention. This is like a square root of x squared minus a, right? Let's see what we yeah, okay. So the integral of dx square root of x squared minus 4, for example, right? All right. Then we recall the formula. We have here secant square theta minus 1 is going to be tangent square theta. So therefore, secant theta square minus 1 is going to be tangent theta. But remember, we have the definition of it, right? Theta is greater than pi less than 3 pi over 2. Okay. Tangent theta is going to be positive here. Okay. So now we can use a substitution. Let x to be, instead of secant theta, I have to use a 2 secant theta. Okay, that's very natural, right? Then x squared minus 4 is going to be 4 secant squared minus 4. So which is a 4 tangent square theta. Okay. So that's why, and also I needed to take a look at dx, right? Dx is 2. Derivative secant theta will be tangent theta secant theta d theta. All right, let's put everything into the integral. The integral becomes 2 tangent theta secant theta d theta. And the denominator is a square root of that. That's 2 tangent theta. Okay? All right. So after you simplify, you will get integral secant theta d theta. So the question is, how do you evaluate this? Mm-hmm. Right? How do we evaluate this? It takes several steps, right? Continue, integral of the secant theta. Right, integral of secant theta. There is a formula here already. Somebody got it. Okay, so integral of secant theta. If you don't have it, it's going to be like that. It's the integral of it's 1 over cosine theta, right? Okay, I have to continue work on this, right? So what I'm trying to do is as a special trick here. You multiplied by each term by cosine theta. Then cosine square can become sine square, right? And the cosine theta d theta. Okay. Then you know what this substitution can use, right? You let W to be sine theta, okay? Then dW is going to be cosine theta d theta. So this becomes 1 minus W squared dW. And we have the formula for this, okay? The integral for 1 over 1 minus W squared, right? So we can take a look at, okay, this is a cotangent, arccotangent, well, it's called the inverse of hyperbolic tangent x, okay? This is called the inverse hyperbolic tangent, right? So it's plus W. Another form for that is because we already have the formula. So this is going to be half of, or half of the natural log of 1 minus W, 1 plus W, 1 minus W. Okay. Yeah, you can always find find this plus constant. So the next step, you have to figure out what is W, right? W is going to be W. W is going to be sine theta, right? It's a sine theta. Okay, if you use this notation. Okay. Now what is the next step? So you see, what is our original substitution? Original substitution is this one, x equals 2 secant theta, right? Secant theta is 1 over cosine theta. Right? 1 over cosine. So you know cosine theta. This is not cosine, sine. Okay, so where x is going to secant theta. So you have to replace x by Yeah, you have to replace x by you have to replace sine theta by x. Okay, this is then you get a final answer. Yes. Okay. So the easiest way to do is just replace it by, sine theta can be replaced by, think about this, okay? So secant square, it's square, right? It's going to be 2 over cosine theta. So cosine theta is going to be 2 of x, right? 2 of x, all right? So how can you change sine to cosine? You know that, right? It's going to be, there are many forms you can get here, right? Then sine theta, and remember sine theta, our theta here, when we take our theta is actually is a between theta and pi over 2 and pi and 3 pi. So when it's positive, that's when it's negative, so be careful. Okay, if you assume that x is positive, if you assume that x is positive, then this will be just the square root of 1 minus cosine square theta. Okay, so otherwise it's plus minus. Okay, so let's see. Okay, it's plus minus, and you will get 1 minus 2x squared. Now, when you take x out, okay, this x squared minus 4, right? Divided by x squared. So when you take x out, you will see this sign is really matched with the x, so you can get rid of the negative sign. Okay, when x is negative, and then when then the whole term is negative, because sine theta will be negative. Okay, so that's anyway. So this check why it is, right? So then you plug them into the formula here as an expression. So you will get 1 plus x squared minus 4, 1 minus square x squared minus 4. Okay, plus c, and then you simplify a little bit, and you get x plus. You can simplify it further, but I stop here. This is an answer slightly different from what is given in the book, but it's very natural. It's step by step. But this is not in the book. Okay, they already gave you the formula. Okay, this even can be written in the form x plus x squared minus 4. Okay, minus 4. Okay, and why this is true? Okay, why this is true? Well, this is you just rationalize the denominator. Okay, if you rationalize the denominator, you will see why this is true. Okay, so there's 1/2 here. Yeah, this is a good exercise, but I think this is already correct. Okay, it's not necessarily in the simplest form. I'm going to go back to this problem again. Okay, is there any way we can solve it using another substitution? Well, we know that hyperbolic tangent x, hyperbolic sine x also have a very nice relationship. Okay, for example, we have the few identities, right? Hyperbolic sine x, cosine x minus hyperbolic sine square x equals 1. Okay, then you have 1 minus hyperbolic sine tangent x equals hyperbolic secant square x. So pretty close, right? So that means yeah, then let's see, another one is a cotangent, I think. Yeah, so this is tangent. So you can have 1 minus hyperbolic secant x equal hyperbolic tangent x, okay? But I have an x squared minus 4. I should get x squared minus 1. So when I divide both sides by cosine, so it's, you see this is one. Another one is by hyperbolic cotangent square x minus 1 equals, okay, hyperbolic cosecant square x. Okay, so that's another one. Okay, and it's pretty similar to this, right? Okay, so it's natural to introduce another parameterization, another substitution. So I can let an x to be, I have to put a 2 here because that's 4, right? And the hyperbolic tangent, hyperbolic we can use, no, we probably don't use, make this simple. I also have this above identity, okay? So this identity, look at, this identity, I don't need a hyperbolic, right? This identity, I have a hyperbolic cosine x minus 1 equals hyperbolic sine x, right? Right? Or I can use, I can also use hyperbolic sine x in the future plus 1 equals hyperbolic cosine square x. So look at our expression. Yeah, tangent is more complicated than tangent is, cotangent is more complicated than hyperbolic sine and cosine. So let's let x to be hyperbolic cosine t, right? So if I use that, then dx is going to be hyperbolic sine t, right? Okay, right? dt. So the above integral here is hyperbolic sine t dt. And the inside, it's twice, I'm sorry, I keep forgetting twice. Inside I get 4 hyperbolic cosine t squared minus 4, okay? So how can I simplify? Because this becomes hyperbolic, right? Hyperbolic sine, right? So it's going to be, okay, let's take a 2 out, and then the square root of hyperbolic sine squared t and dt. And then you remove the radical, and after simplifying, just equal to 1 times dt. So it's just t plus constant. Oh my God, right? So t plus constant, right? And that, what is a t? Well, the relationship between x and t is here, right? So, right? So that is why you can put the inverse here. Okay, now that is answer, right? But this can be also expressed in terms of x in the usual notation, because this was given. Okay, it's half of this plus half of x squared minus 1 plus constant. Okay. How do you get this? Like the inverse function, the inverse of hyperbolic cosine x can be expressed in terms of natural log. Okay, that's just because by definition, right? It's going to be half of, right? First of all, it's cosine hyperbolic cosine x, right? But this is going to be e to the x plus e to the negative x. So you can solve for x. Okay, x is going to be this. But when you solve it, as a, using as a quadratic equation, and you end up with natural log y plus y squared minus 1. Okay. All right. Well. All right. Yeah, it's getting complicated. Let's take a look at this one. Yeah, let's take a look at this problem. How many ways you can solve it? How many ways you can solve the problem? Okay, so let's go through the formulas we already learned. Okay, trying to find the similar. Oh, we find it. Okay, so if you know, if there's a formula in the textbook, actually, you can, yeah. So, that's on the page 488. Okay. The formula, yeah, let me copy the formula, okay? Okay. Page 488. Okay. I have this formula, the derivative hyperbolic, well, cosecant. That's not the usual formula. Okay. Not, yeah, hyperbolic cosecant x. Okay. It's going to be negative about 3x and x squared plus 1. Now here we assume x is positive. X could be positive, could be negative. Okay, so that means it depends on the sign. Okay, so if you assume x is positive, just assume it positive. Okay, we assume that x is positive, then this integral is going to be, yeah, that is negative, right? Plus constant, right? Right, that's it. It's very simple. Now, you have to find the formula maybe in terms of yeah, using natural log, you can find the formula. Okay, if you use a formula using natural log, what you can get. Okay, well, hyperbolic cosecant x, right? Hyperbolic cosecant x is going to be, by definition, right? It's going to be 1 over hyperbolic sine x, which is going to be 2 over e to the x minus e to the negative x, right? So this is a y, and can you find x? The answer is yes. It's going to be 2 over y, right? Okay, then let's find this formula, right? The inverse function. Then you multiply both sides by e to the x, so you get this quadratic equation. All right, so you get this quadratic equation. This is a minus 1. Okay, then you solve for e to the x. Right, it's going to be plus minus 2 over y square minus 4ac, so plus 4. All right, so so you have to make choice. So it should be plus or minus, right? I think it should be plus because minus here, y is a positive. We assume x is positive, right? We assume x is positive, so y is positive, okay? Yeah, because we just assume x is simple. We assume x is positive and y is positive. So e to the x should be, okay, 2y. I think 2 is also canceled out. Okay, it's going to be plus, okay, square root of 4 plus 4y squared, and then cancel 2. Okay, so that is the e to the x. So x is going to be natural log, right? So that is my hyperbolic cosecant x, right? So that is, okay. So we go back to our expression, final expression, here's x. So the answer is going to be negative, okay, negative, yeah, this is going to be, right, plus constant, it's negative, natural log. All right, so this is answer. Okay, now you can express it, right? Get an answer. Okay. So is there any other way we can solve the problem? And this is an example. We try several ways to do. All right, so let's go back to this problem, right? Let's go back to this problem, and remember x squared plus 1, right? We have the trigonometric substitution, right? This is going to be x can be, its nature x could be, you can try x to be tangent theta. The reason is x squared plus 1 is going to be tangent square theta plus 1 equals secant square theta. That's why you can get rid of the radical. So it's very nature idea. Okay, it's going to be square, just equals secant theta. Okay, so then the integral, let's simplify the integral. The theta and the derivative of x, right? That's going to be secant square theta d theta. Okay, so let's simplify it. I get yeah. So tangent theta is here, right? And derivative of, so you get secant theta tangent theta d theta, right? And then after you simplify it, secant theta, okay, is going to be 1 over cosine theta. Tangent theta sine theta over cosine theta d theta. So after you simplify, it's just equal to 1 over cosine theta, 1 over the cosecant theta. Okay, yes. The question is, how do you evaluate this, right? And no, I think we did that right before, right? So there are many ways to solve. Okay, we already given the formula, but if otherwise you have to use another substitution, you know. So this is let me write down the formula. Okay, this is given in the book. Right? Yeah, the integral of a cosecant theta is this. If you don't want, if you cannot use this formula, then you have to you have to do the same way like we did for the secant theta. Okay, we did it at the very beginning. So anyway, x is tangent theta. Okay, x is the tangent theta. So cosecant, yeah, x is going to be tangent theta. So that implies, okay, cotangent theta is going to be 1 over x, right? Also, you want to, yeah, we already get this part. And the cosecant theta, because cosecant square theta is 1 plus cotangent square theta. So it's 1 plus 1 over x, x squared plus 1 over x squared. So cosecant theta should be square root x squared plus 1 over x, okay? And it could be plus minus, but it's a sign matches theta and x, okay? So you plug them into the formula, into this expression, and this will be square root x squared plus 1 over x minus 1 over x plus constant. Okay, so we get exactly the same answer as I did use a different approach. Okay, the expression is slightly different, but it's essentially the same. All right, so we have yeah. So compare with the answer we have here. Right, there's a slightly different. This is negative, natural. Okay, negative. Do we have a negative sign? No. Okay. It's plus. I have a minus. Okay. Now actually the same. Okay. What they do is you rationalize the numerator. Okay. Then I'm trying to show you this is the same. Okay. I'm trying to show you why it's the same. All right, so the reason it's the same is you multiply the numerator by its conjugate. I change the sign. Okay. Then the numerator is a square, right? So you get x squared plus 1 minus 1, so it's just x squared. And here's x. Okay. Then you cancel 1x. And then that's what you get, right? But if you want to turn upside down, you have to put a negative sign in front of that. Okay. This is exactly the same answer as we got it before. Okay. This is exactly the same answer. All right. But this is not always a unique method, I want to say. There are many, yeah, this is a problem. We can use several methods to solve the problem. Okay. I probably want to try another method. It's also, I think it's pretty natural. Right. I still have this function, right? Okay. Some students say, well, I don't like to scale x squared plus 1, so why not? Then you let u to be x squared plus 1. Okay. Let's try this. Sometimes fails, sometimes success. Sometimes succeed. It's the 2x dx. Okay. All right, so the above integral is going to be x. I still have x here. So only replaced is this x squared plus 1. And then I have a dx. Dx is going to be 2u dx. Okay. So I got 1/2 x squared square u du. Okay, it's not too bad because then I have a x squared can replace by u by x squared is going to be u minus 1, so it's u minus 1 times square root du. Well, okay, so maybe it's not a yeah, it's not the best choice, right? So I can let square u to be, I try another substitution, let w to be square u. Why? Because I'm going to get this, okay? Not too bad, right? So what I'm going to get here is going to be u is w squared minus 1. And this just the w. Wow, that's great. This is a very familiar integral, right? And we already have the simple formula we can use. Okay, the reason is, yeah, this is remember 1 over w, right? Square, 1 over w square. Yeah, so this is going to be, if we put a negative sign here, 1 minus w squared dw, it's going to be negative. Okay, hyperbolic, inverse of hyperbolic tangent w. Okay, but this also, it is given by another formula, negative half of h log, okay, 1 plus w over 1 minus w. Okay, so you have to put a w back. Right? What is w? W is 1 plus square of u and 1 minus square of u. And what is u? U is u is x squared plus 1. I think I need since our w is positive, is greater than 1. So you have to be careful about this. Otherwise, it's not defined. Okay, it's not defined. Okay, right? Our w is greater than 1. Right? W is square x. So it's not less than 1. We cannot use the formula. Okay, we cannot use a formula. Yeah, we cannot use it. Yeah, we cannot. We probably can. Yeah, we cannot use this formula unless you modify it. Okay, the reason is. Okay, this formula is going to be natural log of 1 plus x, 1 minus x is only true for x less than 1, absolute x less than 1. Okay, otherwise, you see, but our w is going to be, right, our w is going to be square of u. U is x squared over x squared, u is x squared plus 1. So that's why you cannot apply the formula directly. Okay, but anyway, it turns out to be still true in the sense we have to modify this a little bit. Okay, so okay, so how do you do this without using the formula? Right, arctangent, right? Hyperbolic arctangent tangent to this. Yeah. So to do this, what you can do is we are going to enter into the next topic, w squared minus 1. Okay. So you cannot. I just have to put a cross mark here. I cannot expressed in this form. Okay, just think since W is going to be square root x squared plus 1, which is greater than 1. Okay, so however, this is we'll end to the next topic, right? So what we can do is we can do the following. We can separate them, okay? And then you will get W minus 1 minus W plus 1 divided by 2. Now, this technique we're going to learn in the next, I think it's somewhere, yeah, in the next class, okay? Then you will see that it's going to be natural log of W minus 1 because W is greater than 1. We know that ahead of time. And W plus 1, okay? Okay, then you combine them, okay? Then it's going to be natural log. What is W? W is going to be square root x squared plus 1. Okay, so we get something, all I have to do is switch the order here. See, all I have to do is then it changes the sign, okay? It's pretty similar to this expression. The only problem is this is going to be negative. You cannot put in the natural log, right? That's the only problem, okay? But it's very similar. All I have to do is switch the, we switch the order, okay? We switch the order and yeah, that is co-reductance, okay? That is co-reductance. Okay. So we now we have to use a method we call the decomposition of decomposition of rational function, okay, and decompose it into two simple ones and combine them together. Then you can evaluate the integral for each of them. Well, let's try one more. The makeup quiz will be given to the next class, okay? Okay, integral this, okay? So what is the natural substitution we can use? Well, the natural substitution, still use a trigonometric substitution. Try that first. So according to the book, right, we know that secant square theta minus 1 equals tan square theta. Okay, so that's why you have to use a substitution, let x to be secant theta. Okay. So let x to be secant theta, then be careful about the because then theta is going to be secant, the inverse of secant x. So that's why in order to define the inverse, where's my file? Keep it going away. All right. So theta must be in the interval, right? Theta must be in the interval between 0 and pi over 2, and between pi and 3 pi over 2. Okay, that's a restriction of theta. Otherwise, you cannot inverse it, right? All right. So now let's try. Okay. So the integral becomes square root of, yeah. Okay, the derivative of dx is going to be, right, is going to be tangent theta, secant theta d theta. So we hope we can simplify. The integral square root of secant square theta minus 1 is tangent square theta. So it's going to be just tangent theta, and secant theta d theta. Unfortunately, we cannot simplify. Okay, I get tangent square theta and secant theta. It's too bad. Okay. So can we solve it? Okay, now we cannot solve it. Okay, use a sine and cosine if it's this way. There's no way, it's too complicated. It's going to be like here's a cosine sine square theta, sorry. Yeah, if you're not familiar with tangent, then you get change the sine square theta, and here cosine cube theta d theta. Okay, cube theta d theta. Right? Now, if you try and use this, you end up with this. Now, what is next step? Okay. What is next step? And then you, okay, then you say, I'm going to, let's see, cosine cube I don't like, so I can put cosine to the fourth, right? Sine square theta and cosine theta d theta. Okay, so I can use a substitution, let W to be sine theta, okay? Then dW equals cosine theta d theta. That's okay. So it's going to be W squared, right? And this will be just dW, right? How about cosine to the fourth power? It is going to be 1 minus cosine square theta, then square. So you change the function with radicals into a rational function. Now, technically you can solve it, but that will be next topic. Okay, in section, you can use a method in section 7.4. You can evaluate this integral. It's a polynomial for another polynomial. So this can be like that. 1 minus W squared, 1 plus W squared, and yeah, you can evaluate, okay? So you can, yeah, so by method in section 7.4, okay? So I cannot do this here. Now what you can do and try different substitution, okay? You can try different substitution. Maybe not instead of a trigonometric substitution, you can use a hyperbolic, okay? Because hyperbolic cosine t minus hyperbolic sine square t is going to be 1. So if you want to evaluate this integral square root of x squared minus 1, right? It's possible use this identity, right? Right? It's use this identity. So you let x to be hyperbolic cosine, then probably much simpler. Okay, so dx is hyperbolic sine t dt. So that's going to be square root of hyperbolic cosine t minus 1, and dx is hyperbolic sine t dt. Okay, so finally, this becomes hyperbolic sine t, then hyperbolic sine t dt. So what you get is you get hyperbolic sine squared t and dt. Okay. Then the next question is, then what? Right? Then what? I think the problem can be easily solved because hyperbolic sine t is a simple function. Think about it. Hyperbolic sine t is going to be e to the x plus minus e to the negative x. So when you square it, even much simpler, okay? Plus e to the negative t x minus 2. So you can evaluate each of them. Then you change it back, okay? So you can also write it in the following way. It's going to be half. It's like a double angle formula, okay? It's minus 1, okay? So this is a hyperbolic cosine 2x minus 1 by 2, okay? So you change it to, okay, and then find the antiderivative above 1. So antiderivative above 1 is hyperbolic sine 2t divided by 2 is minus 2, okay? 1/2 of t plus constant. Then from here, you express it in terms of x because your x is hyperbolic cosine t. Okay. And then how do you change it to this? Okay. Okay. So you can solve the problem. Okay. Hyperbolic sine 2t can be changed to you see, just replace this, right? Hyperbolic sine 2t, hyperbolic sine t, that's their relative. Okay, our substitution is hyperbolic, yeah, x is cosine t, where x is hyperbolic cosine t. Okay, so t can be replaced by hyperbolic, okay. Yeah, sine. Yeah, there are formulas for the hyperbolic sine 2t. Hyperbolic sine 2t is, I think it's still the same as twice hyperbolic sine t, hyperbolic cosine t. Okay. Yes. Okay. So you get and minus t plus c. So let me put the details. So this is a sine. Sine is using this identity. Sine is a hyperbolic cosine, right? So it's going to be x squared minus 1, and this is x minus half plus constant. Okay, so that's the answer to the problem. It's not a trivial. All right, so I'm going to stop here and give a minute when if you really want to take the quiz.